In the second video this week, I'd like to talk about normalization. It's kind of come up implicitly a couple of times. Let's think about it a little bit more explicitly in this segment. And the key to normalization is that what we're trying to do is come up with some kind of common reference space so that we can combine data across participants, right? It may be that we're just going to do it in a standard space so that we can show the activity on an individual's anatomy, but in a standard reference plane. So that is to say, where we make the sort of Cartesian coordinates that we use the same across individuals so that we can compare. You do, with realignment, you're using image registration, but you're not doing it in a sort of normalization sense because you're only worried about that individual. But in contrast, anytime you're going to do a group level analysis, that is to say you're going to collect data from more than one participant and combine them, then you need to take into account the fact that their brains aren't the same size, shape, orientation, etc. How do you link them together? What's the right reference frame to use that doesn't bias your analysis? So normalization is this process of registering to a template. So rather than saying we're going to arbitrarily pick the structural scan or the first functional scan or something like that as our reference image, we're going to pick something that's unbiased with respect to a group, and we're going to call that a template image, right? There are multiple standard options that you can use. The first comes from Talairach and Tournoux, who are two neurosurgeons, and there's a particular atlas. The more common one at this point is the Montreal Neurological Institute. They offer a number of different atlases, but there are also various custom atlases that you can use as well, and we'll talk about why you would use one versus another in a minute. So let's start with the Talairach Atlas, because this is where functional neuroimaging really got started. Just in brief, Talairach and Tournoux were neurosurgeons. They were not people doing PET scanning or MRI scanning. The problem that they were trying to solve was if you're doing functional neurosurgery and you have to, for instance, lesion a particular part of the deep brain, how do you make sure that you get your electrodes into the right part of the brain so that you're affecting, destroying the cells in the part of the brain that you want to affect as opposed to something in another part? And this comes into account with something like deep brain stimulation in Parkinson's patients. In some patients who are, resistant to L-DOPA treatment, they sometimes benefit from deep brain stimulation, and it's important to get the electrodes into parts of the substantia nigra, which is a deep structure, right? But how do you know where that is exactly? I mean, everybody's head is slightly different. The shapes of their brain are slightly different. Before you could routinely get a good MRI scan, neurosurgeons still had to do this. And the solution that Talairach and Tournoux came up with was to create this reference frame. And this is the thing that we've borrowed in neuroimaging. So what they did was very clever. They came up with this atlas, and they created what they called a standard set of coordinates. So they were the ones to introduce the idea that X is left, right, Y is front, back, Z is up, down. And moreover, what they did was they said we can even create a 0, 0, 0 point. We can create a starting point that's consistent across individuals. And what they did for that was they said, look, it's going to be on the midline. Midline's going to be 0. So X is 0 means midline. Y is 0 is going to be where your anterior commissure, which is one of the white matter paths that link the two hemispheres, intersects that X equals 0 plane. Okay? And the problem is that still doesn't tell you where your head is in terms of rotations. So what they did was they said, well, if you take the anterior commissure and the posterior commissure, which is another one that's a little bit further back, and you put those on the same plane, then they become 0. Right? So the 0, 0, 0 coordinate is the midline where the anterior commissure goes through this midline plane, assuming that the posterior commissure is also on that plane. And that gives you a reference frame that's consistent from head to head to head. So that's really good. Now, the problem is that heads vary in size and all the rest of it. So we've dealt with orientation. We haven't dealt with the fact that people's brains are different sizes. And what Talairach and Tournoux did that was very clever was they then built in a sort of a system that allowed you to take a certain set of measurements and then scale their system. So if you knew that you were going to try to get something into the lenticular nucleus, which is shown here in this particular image, then you could say, well, it's these certain coordinates in this reference brain, and then what I do for my my participant is I would measure their head, scale those, and that would give me a new set of coordinates that I could aim for using a stereotopic surgery. And this was a very effective and revolutionary approach. What we've done in imaging was borrowed this approach and particularly used what's called the Talairach space. That is this idea that there's this reference space where there's a 0 point as described, and you can have the dimensions in X, Y, and Z so that we can relate across brains using the same coordinate system. What we have not really done, or we did initially, but we haven't done it for a lot of years, is use their actual atlas as an example of the reference image. It was based on a single hemisphere of a particular French woman. The other hemisphere is done using I think a left hemisphere, yeah, and the right hemisphere is simply a mirror of the left, and we know that that's just not true. And any individual brain is full of idiosyncrasies, so it's not a good template. But as I said, what we got out of this was the Talairach and Tournoux space, this reference plane. And here you can see the anterior commissure, which is the 0, 0 point on this plot. You're clearly looking at a midline section of the brain. And the posterior commissure, as long as it's still on the same plane as the anterior commissure, then that's the 0 line, right? That's 0 in Z. Everything below it are negative, everything above it are positive. For Y values, so front to back, everything in front of the anterior commissure is positive, everything behind the anterior commissure is negative. And for X and Y, or X, excuse me, left and right, then everything on the left is negative, everything on the right is positive. Just by convention, okay? All standard space templates use this space. There's nothing different across the spaces with respect to this. Now, one of the things that Talairach and Tournoux did was, in addition to including the sort of outline of the brain that they had dissected to use for their atlas, they actually included the Brodmann's areas that they thought corresponded to those particular regions of gyral and sulcal boundaries. Now, it's worth noting that this image, literally, is the only image that Brodmann left us of human Brodmann areas. Now, if you go back to his, I think it's 1905 book, and I have a copy in my office if you want to borrow it and have a look, he does describe a lot of these areas, particularly in other species, but he describes them a little bit in humans as well. But this is what Talairach and Tournoux had. They looked at this image, they looked at those hemispheres, and they manually said, okay, I think this looks like a prefrontal region. Let's call it area 8. Now, therefore, the Brodmann areas that you can get out of a Talairach and Tournoux book are at best a very, very rough guide. The truth of the matter is, if you're interested in Brodmann areas, this is not a good way of doing it, right? So Brodmann areas are defined on cell cytoarchitectonics, and you don't have that data as a result of doing imaging. It's much higher resolution than you get through fMRI or even high resolution structural imaging at this point. There are other ways to try to get Brodmann's area information into your studies, and we'll talk about some of them, but using the Talairach Atlas is an exceptionally poor choice. Don't do it. And as I said, right, so it was based on the left hemisphere of one 60-year-old woman. It has an odd shape, but everybody's individual hemisphere has an odd shape. So there's not like a canonical shape that you get out of particular heads. The right hemisphere is just simply a mirror of the left because they only actually bothered to do the anatomy of the left. And no major software packages use the Talairach and Tournoux Atlas as a reference when doing normalization. Many of them refer to the Talairach and Tournoux space, but the atlas that they're using is a Montreal Neurological Endless Atlas. It's just the coordinate system from Talairach and Tournoux that they've kept. So the thing that most groups use is from Montreal Neurological Institute. And the first example of this was known as the Montreal 305 brain. Okay, so Montreal sort of recognized that trying to use Talairach and Tournoux as an atlas was a mistake. It didn't really represent variability in the population, and you needed something more than that. So what they did was they were scanning participants back in the 90s with MRI, and they took 250 normal healthy brains and they manually rotated them into that Talairach and Tournoux space, and then scaled them to try to match up the edges, the outer edges of the brain. And this was a sort of a painful manual process, but that was all that was available at the time. Once they had about 250 and they could create an average of that, they used that as the reference image, and they created an automated method of doing the same process and added another 55 subjects. And at that point, they had created what was called the MNI 305, right? So there were 305 normal, healthy brains. These were done in Montreal, so they reflect the sort of variability that you see in Montreal. So that is to say they were mostly Caucasian. There was some non-Caucasian brains. They were all adults. There were no kids. They were not anybody with neurological disease, stroke or dementia, anything along those lines. But the aim there was to create this representative template of a population of normal healthy brains. And they achieved this. This was a significant step forward in neuroimaging because it provides a reference that's now, I'm not going to say completely unbiased because there are some biases there, but it is far, far better than that single one hemisphere from one 60-year-old alcoholic French woman, which is what Talairach and Tournoux used. Okay. Since then, there have been multiple versions of the MNI Atlas, and the one that's almost consistently used across packages these days is an MNI 152. So this is based on a different sample of 152 subjects that were registered to the 305 sample, and they've tried to get rid of, again, some of the additional biases. But whether they explicitly say it or not, all major software packages for doing fMRI analyses use the MNI 152 template as their template for brain normalization. They do it in slightly different ways, but the reference point, we talked a lot about reference points, the reference point for normalization will be this MNI 152 because it's intended as a population sample. To just give you a little bit of a feel for how it differs from the basic Talairach Atlas, this is the same plane through on the Talairach Atlas and through the MNI 152. Right, and the first thing that hopefully you can see is there are lines at the top and the bottom of the neocortex on the Talairach Atlas, and those are continued in blue on the right. And you can see that the MNI brain is bigger, right? It's actually higher, lower. It's a little bit wider. It's larger than the Talairach brain, and in fact, it's not even something that you can address with very simple scaling because it's larger more in certain areas than in other areas. So the original scaling parameters that Talairach and Tournoux offered in the late 80s turn out to be not especially, they're not as accurate as they could be by using a more complicated conversion scheme to link Talairach values to Montreal Neurological Institute coordinates. There's no accepted way of doing it, right? So there are various transformations that people have made available. They all work to some degree, but they're not identical to one another. So there's no accepted, agreed upon method for converting from a Talairach reference frame to an MNI reference frame or vice versa. So I would discourage anyone from even trying to do it. Everything in modern neuroimaging is done in the MNI space. You're talking about MNI space. If you're interested in things that were done with Talairach space, then you're looking at things that happened 10, 20 years ago, and that's well and good. You definitely don't want to discard some of the pioneering studies. However, there is no easy transformation from one to the other. This is an example that David Van Essen and I can't remember Durker's first name, did a few years ago where they were looking at how much you would have to distort different parts of the brain to move it from Talairach and Tournoux into Montreal Neurological Institute. And they've just color-coded it. So the closer you are to the 0 point, the 000, which is along the midline, the less you'd have to change anything. Things become more significant as you move further away. And you can see that in the sort of warmer colors. So like at the level at the anterior temporal pole, you're moving it more than a centimeter to get from one place to another. Whereas in contrast, sort of stuff around the Sylvian fissure is sort of around 4 to 6 millimeters, and their frontal cortex is actually even less than that. So this is what I mean. There isn't an easy scale that allows you to link one to another. To do the distortion properly requires a very nonlinear solution, and there isn't an agreed upon nonlinear solution that everyone uses. Okay, so for our purposes, whenever we're doing normalization, there are essentially three spaces that are of interest to us. There's the functional space defined by the EPI data that we've collected. There's the structural space, which is the anatomy of that individual. And then there's the standard space, which in all cases is going to be the Montreal Neurological Institute 152 template in this class. There are other templates that you could use for different reasons. But the images all have, they're different images, they have slightly different shapes, they can have different field of views, they can have different resolution. So that is to say, like the EPI data is normally sort of 3 by 3 by 3, whereas the structural data tends to be 1 by 1 by 1, which is, if you do the math, 27 times greater spatial information than you would get from the EPI. And then the standard space varies depending, you can sample it at different resolutions. So the key is that whenever we do normalization, we're mapping between these three spaces, and we need to find image registration that allows us to take one to another to the third. And the key is we want to take the fMRI data and put it in a standard space so that we can combine those data from across different people so that we can see what results are consistent across individuals.